Uh, so you've probably seen some drone maps, and if not the maps themselves, you might have seen the signs for the no drone zones. Anywhere where the drones cannot fly are an obstacle. So yeah, they may look like this, these geofences, and I took it from the Wikipedia page on geofence. There are several types of geofences. Sometimes people speak about keep-in geofences, like you lasso a region in a plane and the drone should stay, or your operations should stay inside the geofence. But most often the obstacles are these keep-out geofences. So they really define the exclusion zone where the drones shouldn't enter. And of course, apart from the geofences, there are, well, geofences are more or less artificial zones. There are also other places where drones shouldn't fly, as we've seen in the airspace availability lecture. Yeah, procedures, aircraft procedures, terrain. Obviously, you don't want to fly into buildings, and so on and so forth. Anyway, when we are talking about shortest path for drones, quite often we're talking about shortest paths amidst obstacles. And today we will just look at some of the properties of these shortest paths, how they can be computed, geometric shortest paths amidst obstacles, and discuss how they are related in general to drone acceptance and other things. And before we go into the shortest path calculation per se, we will look at something called visibility between points. So we will have this running example here at the bottom of the page. So you have your S, the starting point, your T, the end point of the path, and this red will represent the obstacles. And we say that 2 points in the domain see each other if the segment between them doesn't intersect the obstacles. Okay, so that's the definition. It's quite natural, right? So this point sees this point, while this point doesn't see this point because, well, there is no direct line of sight. So that's something that you would expect. One technical detail which may raise questions is whether the two endpoints, let's say, of an edge of an obstacle, whether they see each other or not. And we will say that yes, they will. They do see each other. So if you're right here on the edge or at the vertex and right here, then yes, you do see each other. And also if you're here in the middle of an edge and here in the middle of the same edge, yes, we say that these 2 points also see each other. So this is the notion of visibility. And now for any polygonal domain with obstacles, we can build the visibility graph. And this visibility graph, well, any graph has vertices and edges. If you weren't in my basic logistics algorithms course, where we looked at graphs quite a lot, well, you may want to look at other places where graphs are studied. Maybe you've done it. Anyway, so graphs have vertices and edges. In particular, for the visibility graph, its vertices are the vertices of the domain, and the edges connect the pairs of vertices that see each other. So this vertex sees this vertex. So there you go. Here is a visibility graph edge. And again, we assume that since endpoints of the same edge see each other, we assume that there is also an edge between the vertices that constitute the same edge. And in addition, we take the starting point and the ending point and add edges from them to all vertices that they see. So edges like this. Okay, so that's the visibility graph of the domain. Essentially all vertices S and T that see each other. Now, why is the visibility, and particularly the visibility graph, are important is because if you want to find the shortest path from S to T amidst obstacles, then turns out that you just have to find the shortest path between S and T in the visibility graph. And here are a couple of simple arguments of why this is the case. Well, first of all, the shortest path doesn't have these curved arcs. right? Because if there is one, well, you can shortcut. The segment is the shortest path between its endpoints. And moreover, if there is ever not a straight connection between 2 points, then there should be a reason for that. And the reason is that the points don't see each other. Because if they do see, then why don't you go directly? Well, if they don't, then there is a vertex of the obstacle on which the shortest path bends. So all in all, the shortest path in a geometric domain consists of straight line edges, straight line segments that go from vertex to vertex. And well, starts at S, goes to a vertex, goes to another vertex, and ends at T. So visibility graph, in other words, visibility graph is rich enough to contain the shortest path between S and T. And now you know how, if you know how to solve shortest path on a graph, for instance, by using dijkstra or any other algorithm for finding shortest path on a graph, then you can also solve the geometric problem because you have reduced it to the problem on graphs, the one that you know how to solve. Okay, that's why visibility graph is important. And in fact, here is the slide that I was using in the basic logistics algorithms course. But in general, the way you can think of Dijkstra's algorithm on the graph is that, well, what does Dijkstra do? It maintains the set of kind of visited vertices, so we can say the vertices reached by shortest paths, and initially it contains only the source, the vertex S, and it maintains labels, and without going too much into all the details of how it updates the visited vertices, you may view Dijkstra's algorithm as a kind of wave propagation from S. So, you know, the wave goes on, and at any particular time, you have this wave front, which is the boundary between what has been reached already, or the visited vertices, and hasn't been reached by the wave yet at a certain time. And you have these vertices kind of close to the frontier, and one of them will be reached next. Well, that's the one with the minimum label, and then its label gets updated, and the wave propagates further, and so on and so forth, until the wave reaches the target, or until it goes through all vertices in the graph. So Dijkstra's algorithm is kind of this wave propagation. And when we speak about the propagation of discrete, of wave propagation in discrete setting, it may or may not make much sense. I was trying to really show you how this wave propagation may look like. On the other hand, if we speak about shortest paths in polygonal domains, this Dijkstra algorithm and wave propagation has a very specific meaning. And here I'm referring to an applet. You have the link from the slides, but I also make a note to add the link from the web page. So here you have a polygonal domain, and you have the starting point, the point S, and you click the propagate. So these shaded regions are obstacles, and you can propagate, and you can see how the wave propagates from S. So there are many images on this one, on this web page, and I'll show you. Okay, now I see you covered this with my zoom. So only look at this one, and I'll explain what's on it. So only in the top left corner. Maybe I'll make it larger so that I can highlight what I want. Yes, so now you only see what's necessary. So there should be a slider somewhere here. Right, here it is, which would show how the wave propagates from S. Again, so the green point is the source point from which you want to compute the shortest path. And now the black are the obstacles and white is the domain. Don't worry about the red curves right now. And you can imagine that this white space is a lake, and the black are the islands, and you drop a stone at the green point, and then the waves start going out of the stone, right? So they go in circles while there are no obstacles. Of course, when they collide with the obstacle, they stop the propagation. When they touch the obstacle, they go around the obstacle. But again, whatever is reached by a certain time t by the wave is something that has shortest path of length t to the green point. So you see how the wave propagates, and then at a certain point it hugs the obstacle from two sides, and there are two paths to the points on this red line. On this, it's called bisector. So here the green is the shortest path, and you see that everywhere here the shortest path goes above the obstacle, everywhere here it goes below the obstacle. And exactly on this red line there are two shortest paths, one going from above, one going from below. So continue with the wave propagation. Yes, the wave propagates and continues to propagate, and then traces another bisector. So now you see that another red line is being hugged by the waves from two sides. So there are also two types of shortest paths. Over here you go above, over here you go below that particular obstacle, and exactly on the bisector you can go both below and above, and so on and so forth. So as the time progresses, the wave propagates, the waves collide, the wavefront changes. But well, this is a really natural thing to imagine this wave propagation until all of the domain is engulfed with the wave. Another view on it is that the domain is composed of grass. It's flammable. And you start in the grass fire, you igniting the initial point, the green point, and then you look how the fire propagates, and the grass burns with uniform speed, let's say 1 meter per second. And this is how the grass would be burned if the fire propagates, if fire wave this time, not water wave, propagates through the domain. Okay, so that's the wave propagation for you in polygonal domain, something called continuous dijkstra. And here on the slide, here on the left, I have this something that is called shortest path map. So you saw those red lines, the bisectors. Here are the purple. So this is one of the bisectors. And depending on where you are, on which side of the bisector you are, you may have different types of shortest paths going to the points, and anywhere on the bisector you have two types of shortest paths that come to the point on the bisector. And then there are also these green lines. Well, they more or less mark the places where the shortest path changes the last vertex before it gets to the final point. So anywhere in here, in this cell, this vertex is the last vertex of the shortest path. Anywhere in this cell, this vertex is the last vertex of the shortest path. Anywhere in this cell, this vertex is the last vertex, and so on. So altogether, the whole area, the domain is split into cells, and the cells differ in the last vertex of the shortest path before reaching a point in the cell. And overall, they give you the shortest path map. The shortest path map is really good for query purposes. If you want to compute the shortest path just to one point, well, compute the shortest path. But if you want to know how the shortest paths to different points go, and which points are kind of on the shortest path on the way to other points, then you look at the shortest path map, and that gives you the full information about shortest paths from a fixed point S. So this source point S is always fixed, to everywhere in the domain. And this is kind of the shortest path tree in graphs. Again, you may remember that the Dijkstra algorithm doesn't give you just the shortest path from start point to end point. It gives you shortest paths to all possible vertices of the graph. And in particular, of course, in the visibility graph here, you can have the shortest path tree to all the vertices. And in some sense, the shortest path map is the extension of the shortest path tree, because it gives you, again, shortest paths from a fixed source to all points in the domain. Okay, so these are two quite important notions when it comes to geometric shortest path. And well, here is an example. So here on the right is a picture from the airspace availability set of slides at which we looked earlier. And in particular, it shows, well, quite a lot of shortest paths between the different points of interest, POIs, as we call them. And you can see how the shortest path, yes, go from vertex to vertex and go to the destination. Okay, so they are again avoiding obstacles, where obstacles here on the pictures, they are these pink or magenta, or whatever that color is. So these are the shortest path, and one thing that we can learn from looking at shortest path and understanding the shortest path they live on the visibility graph, it underlines how bad it is to have the obstacles. So not only that going around the obstacles makes you less efficient, makes your paths longer, essentially it kind of takes away the whole flexibility of the 2 dimensions that you have. Well, in principle, you have 3 dimensions also in the air, but if you're trying to stay on a single level, or even if you don't, even if you consider 3-dimensional paths, then you also have similar hugging of obstacles. But anyway, on a single flight level, yeah, you have all this flexibility, lots and lots of free space, but everybody wants to be efficient. Everybody wants to fly shortest path. And if everybody does, then there is a lot of congestion that is created along the features, the edges, and the vertices of the visibility graph. So as you can see, for instance, this example, yes, the shortest path, they hug the obstacles, they go tight along the obstacles, and of course they go from vertex to vertex, from vertex to vertex. So along the edges and at the vertices of the visibility graph, at the vertices of the obstacles, you will have lots and lots of shortest path going. There will be congestion, and you can quantify it. We don't go into the details, but there are these notions of centrality of a vertex in a general graph, but also in a geometric graph, in a visibility graph, which essentially tells you how many shortest paths go through a vertex, or how many source destinations the vertex kind of has to quote unquote serve, because the drones following its shortest path would go through the vertex. And well, there are many conclusions that you can draw from that. One is that, of course, that for UTM, it's really important to have obstacle-free routing. Direct routing is good in terms of efficiency, but it's also good in terms of safety. And where you have the congestion, there you have higher probabilities of collision, loss of separations, DAA, detect and avoid, conflict resolutions, and all these other things that you don't want to see. If you recall the capacity thresholds, one of the things that you could observe is that, well, the capacity stays high in terms of risk. Well, there is low risk until the number of operations, the intensity of drone operations becomes high. And then when it becomes high, well, you kind of for sure will have collisions, or at least losses of separations. And of course, if you have obstacles, if you have these vertices with high centrality, with lots of shortest paths going through them, you will have congestion much earlier than if you don't have the obstacles. So obstacles, and well, I mean, some of the obstacles are there, the terrain, the buildings, but some of the obstacles, you're creating a geofence, thinking, oh, I want to, make sure that the drones don't fly near me. I'm surrounding myself with a geofence. Well, guess what? There will be all these paths taking the shortest path and going through a particular vertex, creating lots of noise and many other things. So high congestion, many conflicts. The capacity goes down. Again, doesn't matter whether it's an artificial obstacle or the obstacle that was there. Obstacles are not just bad, they're really bad. And just to finish the kind of non-technical part of the lecture, this is the last slide. Again, there is a lot of talk about social acceptance of UTM and UAM operations. And somehow we don't focus on it in this course. But one thing that, one take-home message that we may have is that the fewer geofences, the fewer obstacles we have, the better it is for UTM, also possibly from the social acceptance view. So it is really important to go do all these surveys, go around and ask people and have the community involvement. In fact, I'm pointing at the course webpage, the sister course from CAMI, the Community Air Mobility Initiative. We don't go into details, but you may see how they interacting with the communities. But it should really be more of the interaction rather than giving the communities possibility or the power to decide. So I don't know if anybody did this kind of experiment, but I bet that if you ask everybody, tell me whether drones shouldn't fly, and then you will have all these, reasons for different places for why the drones should not fly here and there and so on. I mean, you probably will not be able to fly anywhere, maybe some very remote areas, but we do want the drones to fly in urban areas. Urban air mobility is the important thing. So yes, society interaction is important. I'm not saying that it's wrong to interact with the society, but we don't really go into details. Well, there are some projects. If you're interested, then yes, of course, that's an interesting topic. You can see more in this course that I already mentioned. But per se, we don't do much of societal interaction in this course, as important as it is.